Welcome. I'm Robert Brown from the Physics Department of Case Western Reserve University, and I'm proud to open this first session of the symposium on the Standard Model at 50. In this session, it's going to be our pleasure to hear about the origins of the model, from the discovery of quarks to the discovery of the Higgs boson. I guess we'll talk about the Higgs boson first, and the related concepts. And we're going to hear about them from pioneers in these developments. It will be my honor to introduce the speakers, and before the lectures, it's also my honor to introduce the important people who supported the symposium and made it possible. Let me first introduce Dean Cyrus Taylor of our College of Arts and Sciences, himself a particle physicist working notably in both theory and experiment. Dean Taylor wants to welcome you too, so please join me in greeting Dean Taylor.
Yeah, thank you very much, Bob. My attire notwithstanding, I am indeed a particle physicist. And it is my great pleasure to welcome you to Cleveland, to Case Western Reserve, and to this celebratory symposium on the Standard Model of Particle Physics at 50 years. Now, to the best of my knowledge, the term Standard Model was first coined by Bram Pais and Sam Treman in 1975 in the context of a four-quark electroweak theory. I was a senior in high school at the time. So if I may speak personally for a moment, I turn 60 next month. Particle physics, particularly the creation, development, elucidation, and validation of what we now know as the Standard Model, has been central to my life, as I know it has been to yours. For me, some of you have been role models and scientific heroes of mine since I was a kid. Some of you have been teachers and mentors when I was a student. Some of you are or have been colleagues and collaborators of mine as a physicist. Some of you I have in turn taught, and others of you will be the next generation of explorers in this extraordinary enterprise. I think we'd all agree that it's not too much to say that the work we'll be discussing at this meeting constitutes one of the greatest scientific and intellectual accomplishments of humanity. And it's not too much to say that in the process of exploring this physics, we have, as a field, pioneered technological innovations that have changed the world. Indeed, it was 25 years ago that CERN provided the world with essentially a royalty-free license to use the World Wide Web. So I'm thrilled that you're all here to celebrate what has been accomplished and to survey the unexplored vistas that lie ahead. Now, before Bob introduces the next speaker, I would like to thank the people that have really made it possible. These include donors that have been critical to the success of it. So I'd like to thank Richard Morrison, Joseph and Nancy Keithley Family Foundation, Michael Lubin, John Martinchek, Patrick Amon, and Ann Teradon, Anonymous, Keithley Instruments, Mitchell's Homemade Ice Cream, College of Arts and Sciences at Case Western Reserve University, and the Department of Energy. Thank you all very much for being here. I look forward to a great couple of days.
Thank you very much, Cyrus. Another strong supporter of this symposium is our own physics chair. Professor Kathleen Cash would also like to add her words of welcome. Please join me in greeting Professor Cash.
By way of introduction, I want to indulge myself by describing just a little bit about the physics department. It's a relatively small department. It has some notable history, nevertheless, starting with the Michelson-Morley experiment, performed not so many steps from this room. Other Nobel Prize winners who touched our department include Frederick Reines, who was our chair in the 1960s, and Polycarp Kusch and Donald Glaser, who were undergraduates here. Many of us still miss another name you may recognize, Leslie L. Foldy, who was a faculty member here from 1948 until his retirement in 1990, and was a beloved presence in the department well beyond that time. More recently, members of our department founded the Lux Dark Matter Detection effort, now at SLAC, shared in a Patent for Humanity award from the Obama White House for the invention of a cheap, portable, robust malaria detector, demonstrated the manipulation and detection of the states of a single electron spin at room temperature, a potentially important step toward the realization of quantum computing, and developed a biosensor 1 million times more sensitive than the previous state-of-the-art, now in testing for early cancer detection. As proud as we are of the accomplishments of the members of our department, many of whom are here, our former students, others of whom are here, and our colleagues who have passed through, we are especially proud and honored at your presence here, and to welcome you, our distinguished guests, our friends and colleagues, to this celebration. Thank you so much for coming, and welcome.
Thank you very much, Kathy. And now it is also a joy to introduce the person who, along with Brian Lynn, conceived and carried out the production of the symposium, Professor Glenn Starkman, theoretical physicist, professor, director of the Institute of the Science of Origins. Please join me in acknowledging Professor Starkman, who will also speak.
And I'm the last person standing between you and who you really want to hear. On behalf of the Institute for the Science of Origins, welcome to the Standard Model at 50, a celebratory symposium. The ISO is a collaboration of scientists here at Case Western Reserve University, the Cleveland Museum of Natural History, and other Northeast Ohio and beyond institutions, advancing the scientific understanding of systems, simple and complex, human and natural, and the applications of that knowledge. It promotes disciplinary, but especially interdisciplinary science across a broad spectrum, from cosmology to cognition, from planetary science to evolutionary biology and paleoanthropology. Last year, the Institute launched the first undergraduate major in origin science in the United States, meant to help prepare future scientists to ask and answer questions across the traditional disciplines, and to serve as a liberal science preparation for students heading into a variety of careers. The ISO is also an active facilitator of scientific outreach to the Northeast Ohio public and beyond. As director of the ISO, but more particularly as an admirer, a student, maybe colleague and teacher, I'm pleased to welcome our distinguished speakers and our other symposium participants, especially the many students and postdocs who are here partially supported by our sponsors, including the U.S. Department of Energy's Office of Science. In conceiving of this symposium, my co-chair Brian Lynn, who unfortunately cannot be with us today, and I had two primary goals: to celebrate the amazing intellectual achievement that is the Standard Model of particle physics, and the people who made the leading contributions to its construction and validation, and to ensure that that history gets passed on to another generation. There are several ways that you can figure out how to navigate the next 4 days. We have a website, artsci.case.edu/SMAT50. Symposium can be found on Indico, for those of you who have Indico accounts, and there is a guidebook app that you can download on your phone. Of course, we also have lots of volunteers who are easily recognized by the light blue SM at 50 t-shirts. Please ask them for help whenever you need some. For our visitors, I hope you enjoy our beautiful campus, visit the museums and gardens that surround you here in University Circle, and especially that you take the time to interact with one another, especially across those artificial barriers of age. Please enjoy the next 4 years. And now I'd like to pass you back to our first convener, Bob Brown. Did I say something funny? Yes, I'm sure I did.
4 years, yes. It's a long conference.
Thank you, Glenn. Jonathan Butterworth is a professor and head of the Department of Physics at University College London. He's a leader in the ATLAS experiment at the Large Hadron Collider in Switzerland, involving the world's largest particle detector. Besides the discovery itself of the Brout-Englert-Higgs boson, Professor Butterworth is involved in studying its properties and winning many awards along the way. He's written 3 popular books on the same topics about which we are fortunate to have him tell us. Please join me in welcoming Professor Butterworth.
Thank you very much for that introduction and for the invitation to speak. I have to say this is a real honor. I feel a little overwhelmed, I have to say, and I, for a while I kind of wondered exactly what my qualifications are being here. I'm actually the same age as the Standard Model. So that could be one of them. As was said, I'm a member of the Atlas collaboration. Interesting, I was actually the convener of the Standard Model Physics Group on Atlas at the time that the Higgs boson was discovered. We did not have, at that time, the Standard Model Physics Group was not responsible for the Higgs boson. There was a Higgs search group. I keep arguing now that we should merge them all together and really have maybe only one physics group at Atlas, but never mind. Anyway, on with the talk. I will not, given the time constraints and given the rest of the program, I will not be covering the history of the search from its beginnings, but I will focus on the discovery, and I think it's also important to give a status report of where we are now with a little bit of a future look. So it will necessarily be a brief summary, and this is another reason this is an honor. It's a brief summary of the work of literally thousands of people, and I have to say, having been involved in public engagement a little bit around the Large Hadron Collider and the Higgs, I think one of the most important messages that we managed to put out there is the collaborative nature and the international nature of science, and the fact that all these people, often with enormous egos, manage to work together and achieve wonderful things. And I think that's an important message to communicate from a meeting like this as well. And then just because I have to do something fun, I want to give some, and partly because of, again, the nature of the meeting, I will give some counter-historical speculation at the end. Okay, so I said I'm not going to talk about the history of the search, but given but then I'm immediately going to show an abstract from, or a quote from a 1976 paper from one of my fellow speakers here. This is the motivation. This is what gets thousands and thousands of people working together to take the data to see whether something exists or not. This is actually a paper from Mary and John Nanopoulos saying we should finish this paper. What they did was characterize the phenomenology of the Higgs boson, which was a very new thing at the time, or relatively new, a few years after the original papers. Apologizing for the fact that although we knew a lot about it, we didn't know the mass, we didn't know exactly how it would show up. But we do feel that people performing experiments vulnerable to the Higgs boson should not know how it may turn up. Luckily, the experimentalists, I guess, ignored this bit for the reasons we do not want to encourage big experimental searches for the Higgs boson. So here we are today. There's, of course, more to the motivation and the theoretical characterization of the Higgs after that foundational paper. And in more detail, this is the kind of map the experimentalists were looking at when deciding what were the important experiments to do, how would you design them, what were the critical performance parameters of the accelerators and the experiments. What this is showing you is the expectation now. Actually, further from that paper, we actually know pretty much everything else about the Higgs boson now in the context of the Standard Model, apart from its mass and, of course, whether or not it existed. And so we could predict then how it would appear in an experiment given a particular mass. And what you're seeing here is the branching ratio, importantly with the error bands, the uncertainty in that as well, as a function of the Higgs mass from essentially just before the discovery. This is from the Higgs Working Group in 2011. But this kind of knowledge had been accumulated over the years in the design and the approval and throughout the history of the Large Hadron Collider and previous experiments. And you see that it changes massively. This doesn't look like a standard smoothly varying bit of physics, okay? You have a low mass. It will couple in general to the most heavy thing. It will decay to the most heavy thing. It has the energy to do so. It has enough mass to do so. So B quarks are very important. but very hard to see. There's a whole bunch of stuff. The tau is the heaviest lepton, so it couples. And then once it gets heavy enough, it will decay all the time almost to W bosons and Z bosons, and then the top quark will kick in at some point. This is when we didn't know where it lived here. There are three of these that really drove the experimental design, and two of these really that drove what went on at the Large Hadron Collider, and those are these two. So in searches at the Tevatron, for instance, the most sensitive channel was BB, and it's extremely challenging because there are many ways of producing a B quark in a collider, particularly a hadron collider. But the real things that drove the design parameters of the LHC experiments, ATLAS and CMS, were maybe not unsurprisingly the Z decay channel, because the Z can decay to leptons, and that's a beautifully clean channel to see if you see 4 leptons coming from that. But also, maybe more surprisingly, the 2-photon channel, because although it's very rare, it is also very clean, and the ways you can produce 2 isolated high-energy photons are much fewer than the ways you can produce 2 B-jets in a hadron machine. So that was our starting point, and that was a starting point for an enormous effort. This is, I'm not even talking about digging the tunnel, because of course that was dug for the Large Electron Positron machine, but this is the start of the excavation of the cavern to put ATLAS in, for instance. This is the tunnel that the Large Hadron Collider now sits in, and the magnetic dipoles that steer the beams around the tunnel. I'm not going to say much about that whole engineering project. I just want to emphasize the size and scale, the determination of will, and the number of years and currency units that went into it. One thing I did find interesting while refreshing my memory of some of the history of this, and of course I was not present for the vast majority of it, is discussions at the time, which some people here will probably have been involved in those discussions, about actually when building the Large Electron Positron Collider, which was designed to study the Z boson, how big would you build the tunnel? And there was a whole bunch of discussion. Obviously, you build it as small as you can and get the job done, unless you're thinking there might be another job to do after that, which might involve putting a hadron machine in the same tunnel. And there was what looks like, I read the minutes of these meetings, I obviously wasn't there, but there looks like a really interesting discussion where a compromise was set up, that the tunnel wouldn't be as wide as the hadron machine fans wanted. So there was no existing magnet technology for hadrons that could have fitted in it comfortably. But they would set a challenge to the hadron, they would build it wide enough so that if you could realize a design where you had the 2 beams integrated in a single dipole, you could actually put a hadron machine in afterwards, and that's actually what happened. This is a cross-section of one of the LHC dipoles with one of the, because these are the same particle, these are not particle-antiparticle collisions, these are both protons, so you need 2 beams, 2 separate beam setups for them, but they're integrated within the same dipole system. I find it fantastic that this kind of discussion was going on, and the amount of vision and future planning that had to go in there, and the combination of realism and ambition that made that kind of thing happen. So this is the result. I always feel duty-bound when I show this picture to point out that they wouldn't let us paint the yellow line on the thing. So if you're flying into Geneva Airport, you don't actually see this. But this is Geneva Airport here, and this is the path of the Large Hadron Collider, and this is the main laboratory at CERN. And you see ATLAS and CMS pretty much diametrically opposite each other on the ring. And these are the design parameters. I'm not going to go through them in detail. But we're colliding beams now at 13 tera electron volts, around 1 billion collisions per second. The detectors are digesting that information, and we're running right now. We're on what looks like being a pretty good year in 2018. So that's all I will say about this enormous endeavor, which is the accelerator. We have a presentation later about accelerators and their impact on the standard model development, which of course is enormous. But I will move on to the detectors, and I also actually will not really do the detectors justice, just to say that they're both ATLAS and CMS, these typically cylindrical shapes with layers of different detector technology. So we have inner detectors primarily consisting of silicon now, both detectors with pixel detectors in the heart and then silicon strip detectors around them. In a solenoid we have a calorimeter, which in actually CMS's case, the electromagnetic calorimeter is inside the solenoid as well. And hadronic measurements, we have surrounding it muon spectrometry, and the magnet system for the muons and for the inner detector are separate and vitally important. And this kind of layout was, as I said, particularly in terms of the Higgs search designed to optimize our possibility for finding, make sure we could identify Higgs to gamma gamma and Higgs to 4 leptons with good resolution. But these are genuine general purpose detectors. They're not built just for those two things. We were doing physics for the first time clear above the electroweak symmetry breaking scale, and we had to be ready for pretty much anything that nature might throw at us. This is a picture of Atlas. The beam comes through here, the things collide in the middle. You see the silicon and the calorimetry around. I think the main point, apart from things I've already said, is just to point out again the scale and the size. These are people here. This is a picture of CMS and the NCAP calorimetry system there. I want to show this one though, because this is, and I'll put in a brief advert while I'm here. This is a CMS cavern. You can see they're all working really hard. This is in fact not CMS. This is it's directly above CMS on the concrete floor above the caverns. The CMS is down below. This is a 1-to-1 scale mural photograph of the CMS NCAP, which is directly below it. It was commissioned by CERN for a TED talk that they did there in the cavern at some point. This is actually the inaugural dinner of the CERN Alumni Association. I recommend any of you who've passed through CERN, work there, or still do, that this is worth signing up for the Alumni Association. They have some really nice events, and it's a good thing. And I particularly like this picture because really you cannot tell that this isn't really CMS. And I think I may lie about this picture at some point in the future. Anyway, these detectors are, again, the main point really is to say that they're enormous undertakings. They're extremely sophisticated. They're pushing technology in all kinds of directions. This is a CMS picture of CMS again in the kind of cutaway design. But again, you see from the outside it looks rather similar to from in block diagram form. It's rather similar to Atlas. It's important to point out that different technology choices were made along the way, so there's a complementarity because these are their own prototype and things can go wrong. So you don't have all your eggs in one technological basket, although we're all very pleased to say that both of them actually did work. That's the physical detector. You also have to get the data out of that detector and the trigger and decide which data to read out of that detector system, and the trigger and the data acquisition are vitally important and equally challenging parts of that. We have about 100 hertz of interesting events, depending on who you ask on what is interesting, from around 1 billion hertz total. And the typical raw event size is order of megabytes, so that's a significant data rate even these days. And remember, these machines were being designed 20, 30 years ago, so it was enormously challenging then. And this is just illustrating the cross sections that we're looking for. So the total cross section for two protons colliding is up here. The cross section for producing B quarks is here, which is why Higgs to BB is extremely difficult signature to realize and to find. The cross section for producing hadronic jets and so on, WW, and then for Higgs equals 125. So James remade this plot once we knew the answer. But you see the different Higgs production mechanisms buried down there, many orders of magnitude before the raw data rates. So this sets the scale of the challenge. The detectors have to be able to be sensitive to this data, but they also have to be able to read it out so the physicists can look at it. And even physicists looking at it requires the solution of a huge number of challenges. So we need fast and performant reconstruction of objects in the detectors, and we also need some of that in real time online so we can decide which events we want to read out and look at in more detail. And we have detailed software models of the detectors, which often are hidden to the theory community, I think. And I just want to point, I love this picture because I want to point it out because it's critical to the particular performance, but it's also an example of the kind of understanding of your apparatus that goes on in a modern particle physics experiment. So we have a software package called Géant, which monitors the known interactions of particles and matter. We build a geometrical model of our detectors in that software package, and we can propagate simulated particles through it step by step with the magnetic field, with all the scattering. And we can use that to understand the data we're seeing. So what you're looking at here is on the left-hand side, if I get this right, because I can, yes, it says simulation here. On the left-hand side, this is the real reconstruction of electron-positron vertices in the Atlas detector, in the tracking detector. And what it's showing you mostly is convergence. So when a photon hits a bit of material, converts to an electron-positron pair, and you have a vertex. And so the more material there is, the more likely a photon will convert. So you end up getting a material map of your inner detector as seen by the inner detector itself from reconstructing the vertices. And this is the simulation in Géant of the same thing. And you see the level of detail. These are you can even see the modules of the silicon strip detector here being modeled properly. And then this is zooming out a bit so you can see all the different layers. And you see where there are more particles, we have a better map. But nevertheless, we have a really good understanding. And we don't just do this for fun. Photon conversions and the material in front of your calorimeter are an absolutely critical parameter in what the resolution of the diphoton mass is, and so have a direct bearing on whether you discover the Higgs or not, or whether you beat CMS or not to discovering the Higgs. So this is going on behind the scenes in the detectors, and then all this information has to be processed and understood, and we have a worldwide computing grid, which, given this picture came from CERN, is focused on CERN, but there's a huge amount of it over in the United States as well, here, and Fermilab and Brookhaven and SLAC are huge centres for that. So that's what's going on. That's the effort, the scale of effort and technology involved. One thing I will say, which I looked at the agenda, and I'm one of I think a minority of experimentalists giving talks here, so it seems a bit daft to put a theory slide in. However, I think you'll hear although you'll hear a lot about the theory later, there's an important element of it that perhaps won't be so well represented, which is this area of Monte Carlo generators, event generators. In order to build this picture, for instance, we need to simulate the physics of the collision itself, and that requires the particle theory. And that's the kind of picture of what goes in there. You have a hard sub-process, you have the proton densities, so describing the quarks and the gluons distribution inside the proton. You have the radiation of quarks and gluons, which you'll hear about in later talks, and their conversion into hadrons. They allow us to make precise, exclusive calculations in fixed order, QCD and electroweak, resummed, matching really state-of-the-art calculational techniques. And they're an absolutely key tool in modern collider physics in general. They're useful in the design of the experiments, but they're also very important in allowing us to compare what we actually measure with what actually is predicted by the theory, and in a kind of more like-for-like basis and some of the more inclusive calculations. And this is just an example of that. This is it doesn't look maybe so precise until you realize that this is the transverse momentum of the fifth jet in a W plus jet event, where the fifth jet is the fifth lowest. There are 4 higher PT jets. So the kind of exclusiveness, multiplicity, complete event description that we have with precision QCD and electroweak now is absolutely stunning, and also essential in the performance we're getting from the experiments. Okay, so this is where we were March 2012. LHC data had already had an impact on this plot, but what you're looking at is the mass of the top quark here, the mass of the W boson here, which are 2 of the less well-known parameters of the standard model. The standard model is a complete and consistent theory in the sense that you can do loop corrections to arbitrary precision, and therefore any parameter in the standard model in principle can be constrained by precision measurements of the rest of it. And what you're seeing here is that a consistency test between the W mass and the top mass. The standard model has to lie within the ellipses, and the Higgs has to exist and has to be within one of these bands here. And this bit here was ruled out by pre-existing LHC data before 2012. The lowest area was being constrained by the Tevatron data, and before that by LEP and other data. And the theory consistency check relied on these meant it had to be within this green ellipse, at least at what is it, 1 sigma. So the tension is sort of palpable in the theory that if we don't find the Higgs here, we clearly have an issue. So this is 2 years of our lives flashing by up here. What you're seeing here is the mass of the diphoton pairs that I described, how we designed the detector to measure them, the number of events. Lots of statistical fluctuation which gradually dies away, and eventually a bump at around 125 GeV, which is a signature that there's a new particle in there decaying to a pair of photons. That was Atlas, this is CMS. Both plots are kind of contemporaneous, although you'll notice that they're both at the end of 2012 running rather than at the point that the discovery was declared. But this is the 4 lepton, the other channel that I said drove the detector design. So two electrons, 2 muons, or 4 muons, or 4 electrons. So basically a signature of a real Z boson and a virtual Z boson coming from the Higgs. And you see here the peak from Z decaying radiatively to 4 leptons. Here, oops, let's let it go again. Here you see a kinematic threshold, which is when the 2 Z bosons can be on shells, so the mass would be 180 GeV. And here in the kind of wasteland in between those 2 features, you see this other feature emerging above the noise, which is at the same energy, same mass as the bump in the previous distribution, the 2-photon distribution, and is a sign that there is a new particle there, and not only is it decaying to 2 photons, it also decays to a pair of Zs. And both of those things are in line with the standard model predictions. So I told you about the precision of our understanding of the detectors. I just want to show this as it's kind of boasting, but it's not my experiment, so I'm allowed to boast about it. This is from CMS. It was shown by Nick in a recent meeting I saw, and I found it kind of impressive. This is from their technical design report, projecting an integrated luminosity of 30 inverse femtobarns, actually at 14 TeV, but the expected discovery significance here for the Higgs boson was around, between 8 and 9 sigma. This is the actual result for 36 inverse femtobarns with their likelihood curve for that, which is essentially giving you pretty much the same significance to within 1 sigma of exactly what they said. And this is the more compelling plot that goes with that, which is the diphoton bump at that significance. So, okay, this technical design report, this is the physics technical design report. So it was written once the technologies of the detector had been fixed, and in fact most of the detector had been constructed by that stage. But nevertheless, that's the level of understanding that is developed and required in order to do, of the detector that is required in order to do this stuff, and it bears fruit. So take the projections seriously when we're looking at the luminosity upgrades and things, I think. So we're in now, I guess, the era of precision Higgs physics. This is what I'm showing here is actually not the latest, because it's from run 1. It's the 8 TeV, and the reason I'm doing that is because it's only from run 1 that Atlas and CMS have actually combined their results. Individual results from here have been updated since, and I'll show some of them in a minute. But these are the best summary plots from the run 1, which was the run in which the Higgs was discovered. And you see what you're looking at here is a combination of the decay modes and the production modes for the Higgs compared to the expectations for from the standard model. So gluon fusion is the dominant production mode, which is annoying when you're trying to explain the Higgs because the gluon is massless, but of course it goes via mainly top loops. And you see the measurements there from Atlas, CMS, and the combination. It can also be produced by electroweak boson fusion, and also in association with a vector boson, a W or a Z, and also in association with TTH, which I'll come back to later. But you see at least the ones where there is a significant measurement are in very good agreement with the standard model and consistent with each other as well, with a scatter that even looks reasonable, that we weren't too conservative about our uncertainties even. And then the decay mode branching ratios, so the Higgs to WW and the Higgs to 2 Zs. We can't measure the total branching ratio because there could be invisible Higgses in there. We don't, in a hadron machine, you don't have full control over the center of mass energy of the collision that creates the Higgs. But nevertheless, you can take the ratios of the different decay modes, so the taus, the photons, the Zs and the Ws, and then the Bs, for which there's not a significant observation there, but you can still do the consistency check. You can ask the question, were those 2 bumps in the 4 lepton and the 2 photon, were they really in the same place? Were they really the same mass? Were they really the same particle? And at least within the uncertainties here, they are. And you can see here, this is now the CMS is the dotted and Atlas is dashed. And Higgs to gamma gamma is red, and Higgs to 4 leptons is blue. And you see that the different measurements, they scatter as you would expect with any relatively low statistic uncertainty, but you see they're consistent, and you can extract a Higgs mass from there, which is indeed just over 125 GeV. And you can start also extracting the parameters of that Higgs, and you can look at the angular distributions of these particles and say, is it really spin zero? Is it really CP even? And this here, for instance, is the constraints on the CP violation, the CP not the CP violation, but whether it's even or odd, and it's coming out as even. So all checking out as a standard model Higgs boson. We now, of course, that was run 1. We do, of course, have data from run 2 now. We have reobserved the Higgs. So this is the cross-section for the extrapolated cross-section for proton-proton to Higgs, where you take the various measured channels and you extrapolate using the standard model to the total cross-section. And you see that it's kind of, maybe we were a bit lucky in run 1 to get it so quickly. I remember Lynn Evans being quite annoyed that we managed to find it with 7 and 8 TV when he went to all the effort of designing a machine for 13. But maybe we were lucky, you know, I wouldn't want it to take that risk. And also, of course, it could have been at higher mass. But anyway, we have it still in 13 TV, and these error bars are going to shrink and more exclusive measurements will be made. This is an exclusive measurement of the transverse momentum of the Higgs, or at least the transverse momentum of a pair of photons extracted from a fit. It's consistent with the Higgs mass. It's important to check these things out because the Higgs is a completely new object in the standard model, a unique object in the standard model. There are no other scalar bosons like at all in there. So how that develops as a function of PT, whether it remains looking standard model-like even when it's being produced well above threshold, is an interesting question to ask. And this is one of the ways you can address that question by having enough of the Higgses now to actually start measuring their kinematic distributions properly. There are the more challenging production modes to chase after. One of the classics is TTH, where you get direct access to the Kawa coupling of the top to the Higgs. Top is the heaviest particle in the standard model. The Higgs is responsible for that mass, so it's an important thing to measure. This is an Atlas extraction of the fit, and CMS recently just went over 5 sigma in significance in this paper here, where you see they've combined. There's a lot going on here. You combine many different decay, the WW, ZZ, gamma gamma, tau tau, and BB decay modes of the Higgs. You combine 7 and 8 TV running, which is the plot point you saw. The point you saw on the previous slide, the earlier slide, and the 13 TV, and you see now how much the 13 TV data are improving things. And in the end, when you put all this together, you peak over the 5 sigma arbitrary threshold for discovery. So this is now discovered as well. The BB I mentioned a few times is a really challenging decay mode to pick out because the production cross section for B quarks is so high. Here you see the Atlas, the latest Atlas results from searching for this, again including 13 TV data with a lot of work going on here to extract the signal. The red here is the signal, and again with an excess around 1.3 TV. It's above 3 sigma, it's not yet above 5 sigma, but it's looking pretty convincing that it checks out with the standard model in that decay mode as well. Sorry to depress you if you were hoping it didn't, but it looks like it does. And this is one I've actually worked on myself, although not the measurement, but on the techniques behind it. Coupling those production and decay modes together, the most common production mode for the Higgs is gluon-gluon, which doesn't have many distinguishing features except that it produces a Higgs. The most common decay mode is BB, which is really hard to pick out from the background. So gluon-gluon to BB is a huge cross-section of the LHC. But if you go to high enough transverse momentum and the Higgs is boosted, then you have the whole of the Higgs's decay products collimated in a single QCD jet with 2 B quarks in it. We understand QCD and jet production well enough now that you can interrogate that jet and do B tagging inside it, and you can pick out first of all Z to BB, where the Z is very boosted, rather compellingly, and then less compellingly, in fact not yet significantly, the Higgs beginning to show through there. And this result from CMS, it's less than 2 sigma at the moment, but the idea that you see the Z so clearly bodes very well that in the end this will be a very powerful channel for looking at the Higgs at the highest PT. This is one of those channels that actually gets better as you go to high PT, and you need the high cross section at high PT obviously because and the high branching ratio because everything falls with PT. So there's a lot going on, there's a lot to do. I'm just going to dip into my alternative history in my last couple of minutes. So this is something I don't tend to read philosophy papers, I'm afraid, but I did look at this one and I thought it's a question I've sort of asked myself. Theory-driven experiments designed and performed in order to investigate well-defined research questions. Now, whether or not the Higgs is there or not is a pretty well-defined research question. It's defined by the work of many people in this room as the standard model is such a well-defined theory, you can pose that. So the question I like, would we have seen it without the standard model, and more specifically without the work of Brout, Englert and Higgs et al. To actually define the question that way? Well, we knew interesting things happen around 100 GeV-ish. These are the results from the electron-positron colliders, principally LEP. So we knew there was something odd going on in nature here. Maybe more compelling is this plot, which is from my PhD experiment on Zeus, where you see the deep inelastic scattering. You see the charge current cross-section here, where there's an exchange of a W boson, and you scatter an electron off a proton, and it converts into a neutrino. Compared to the electromagnetic cross-section, or the neutral current cross-section, where the electron remains an electron. You can measure both those things. The weak force doesn't happen very often because it's weak. The electromagnetic interaction happens more often. As you go up in energy, they come together. There's an electroweak unification scale, and you could hypothesize this was connected with the mass of the Z and the W bosons and so on. So the main point of this is to say we would definitely have decided to go and investigate this region experimentally, I think. And when we'd investigated it, we would have measured this cross-section, which is the differential cross-section as a function of the 4 leptons, even if we hadn't optimized our experiment to do that. And we would have seen the bump of the Z, we'd have seen, let's get my arrows, the bump of the Z, the bump of the Higgs, the bump of the threshold that I mentioned earlier in the animated plot, and the continuum, and we'd have seen that it all checked out. We would certainly have seen the Higgs boson with or without the theoretical guidance. Whether we'd have built the LHC to see it with is a bit more of a question to discuss, but I think once we built it, we would certainly have seen it. There may be more scalar bosons. I'm out of time now, but there may be more scalar bosons. We're looking beyond the standard model. These are some constraints on extra bosons predicted in supersymmetry and also in the exotic particles decaying to pairs of Higgs bosons. Conclusions and beyond, then, it was a textbook-like prediction and discovery after many years of experimental and theoretical work. Textbook-like, I think, actually means incredibly rare. I don't think science really does work that way very often, but never mind. It's the final particle of the standard model. Anything else we find is beyond. It was a fantastic success of the theory, a qualitative new phenomenon predicted from basic principles, and the Higgs mass is a key new physics parameter of the standard model. And I guess that's reflected in the amount of times that word appears in citations on Inspire. So now we're going into the unknown. We need well-defined precise measurements and calculations, high multiplicities, high boosts, even for electroweak scale objects. Looking at even rarer decays, Z gamma, Z to mu, mu is even maybe within reach at the luminosity upgrades. Looking at the off-shell, we have enough precise enough theory that looking at the off-shell and interference effects actually provide important constraints. We're grasping towards characterizing the Higgs potential properly. That would require a measurement of di-Higgs production. We're looking for anomalous couplings, Higgs portals, and so on. There's a lot to learn, and there are many challenges to come. Thank you.
Thank you, Jonathan. We have a chance for a question or two, and I guess we'll pass around a microphone to anybody who would like to ask a question, please. Any questions at the moment?
I'm going to be at CERN this summer as part of just going over to Europe. Are you going to be there, and what time is lunch?
Yeah, lunch is about 1. My son is doing work experience on one of the antimatter factories this summer, so I'll be there late August if that matches your schedule. Thank you. Thank you for the easy question. This one over here.
I just was wondering if you could start working. Yeah,
I think so.
If you could say a bit more about with high luminosity, how much you can do. I know that, for example, the Higgs to see a photon is very challenging because the aberration ratio to lepton is very small. And can you say a little bit more about how much you can do with high luminosity LHC?
Yeah, I mean, I don't have. I should maybe have had backup slide on the prospects, but I don't have one, I'm afraid. I think, if I remember rightly, then Higgs to Z gamma is doable. At the very highest luminosity to above 5 sigma, if I'm remembering correctly. I can't remember whether you have to combine Atlas and CMS to do that or not, though. Higgs to di mu on 3 sigma might be just about reachable with the high luminosity, and I think the same statement for di Higgs is also the same. What's going on with the various vector meson calculations, and actually, so J psi plus gamma, for instance, and whether they actually do tell us anything about Higgs coupling to charm, I think is still not actually that clear, because the form factors and things that you have to put in there, maybe they're not really telling us a great deal, they're just rare things you can pick off, but the form factor dominates. But it might be that there's information from the interference terms in there with the charm coupling, some of the lighter fermion couplings as well in those. So I think there's a lot still going on there, actually. There's a lot of work going on. The European strategy particle physics thing is going at the moment, and I know there are a lot of results on those things expected quite soon. But that's my best memory of it at the moment, I'm afraid. Okay.
So, Jonathan, this is a question that I would say it would be great. We could keep it in the room and we wouldn't tell anybody. But unfortunately, it's being taped.
Yeah, I signed some form, something. Yeah.
Is there anything right now about the decay modes, the masses, any of the branching ratio, anything that you're worried about?
I'm worried about all of them because they're too much in agreement with the standard model. So that's a cheesy answer, I know, but it's true. There's nothing there that is actually causing us to watch it more carefully than the rest in terms of the Higgs, I would say, at the moment. There are, of course, when we're looking at a lot of plots, there are of order a dozen at any one time that we're all a bit kind of twitchy about. But at the moment, if you look at the standard model, the Higgs PT distributions for the Higgs to gamma gamma and Higgs to 4 leptons, which are public, then the standard model predictions are around, they're below. And they're statistically insignificant, but it's systematic and it looks a bit odd. So I'm not at the point of being excited about them, but I would like those theory predictions to be tightened up on, because I'd like the theory uncertainties to be reduced, because we know the data uncertainties will reduce by quite a lot very soon, and that's worth watching.
It's interesting how the words excitement and worry are yeah.
No, worry for an experimentalist is when you think your detector's broken. I think when you think your theory's broken, that's exciting.
Thank you very much again.